Hello again. Now we look at hypothesis testing for population proportion. So this is similar to work we did earlier. There we looked at binomial distribution and proportions, and the testing was for small sample sizes. In fact, it could also be for large sample sizes. But generally speaking, there we were looking at things in terms of exact binomial tests. So if you're looking at, say, a hypothesis to do with one-sided test, P less than versus P equals, of course, so P equals P naught is always the null hypothesis. Less than, we have a p-value that looks like this, x less than equal to x observed. Excuse me. So if we do have, say, an n trials and we get x successes over here, then this is going to be a p-value. If the hypothesis is on the upper side, the right side test, then the p-value is x bigger than equal to. This is in every case, as I would say, is away in the extremes. And if it's a two-sided test, then of course all we do is we take a look at the value of x observed and go to the extreme, either the right tail and double it, or a left tail and double it. And this depends on the tail in which x bar in x observed is. So that's decided easily enough, because, for example, if I have my h naught as p equals 0.5 and my x observed is 7 and my number of trials here is 20. So I'm expecting in this case from the binomial distribution, the expected number is np, I'm expecting 10 on average. 7 is less than 10. So in this case, for a two-tailed test, a two-sided test, if my h1 is that p is not equal to 0.5, then my p-value here, the extreme as far as the tail is concerned, is with respect to 10, should be probability that x is less than equal to 7. And so doubling that is what will give me my p-value for a two-sided test. So let's see some examples. Well, let's get to the real situation here. We're now looking at large sample sizes, and in many cases, especially if you're looking at samples of people, it'll be in the order of hundreds or if not thousands. So we saw earlier in our work on estimation and on sampling that the sample proportion that's in the diet sample proportion is approximately normal not 1 by the central limit theorem. So in this case, all that changes is our p-value is now obtained from the normal distribution. Nothing else changes. Now in most situations, not necessarily just business situations, but this is a common one, sample sizes of 30 or bigger are very common. Samples there will be in the few, in hundreds, generally speaking. As an example over here, a pizza shop advertises that it will deliver pizzas in the local area within half an hour, or it's free, half an hour ordering. And the manager feels that if he can meet this target 90% of the time, then he's making a profit, or she's making a profit. So to test this, 20 deliveries, and 16 were delivered in time here. So here straight away I can find my p hat is 16 over 20, and that's 0.8, 80% only. We're below 90%. It's a matter of deciding from a hypothesis test that is this really below 90% or is it just because of my sample. So here this is simply a test for a binomial proportion based on small samples, and this is based on an exact test. We've done that earlier, so I'll leave that out. You can finish this yourself, and also we can discuss the type 1, type 2 error situations over here. We'll do that afterwards. Here's another example. Arthritis is a painful disease, and so here this is a study on some pain relief by ibuprofen. So if more than 3% of people suffer side effects because of this pain relief, then a stronger warning will be put in the labels. So 440 subjects were given this pain relief, and of these 23 suffered some side effects. So here what should the action be by FDA? Should they actually make the warning stronger? And then we look at assumptions as well. So the first part of this is going to be a simple hypothesis test. We have essentially our hypothesis here is P. It says if more than 3%, so this is saying it is actually 3% or 0.03 as opposed to more than that. Where this P is the proportion of people who suffer side effects. Our sample proportion here, P hat, the observed value of that, we had 23 out of 440. Our test statistic here is the standardized sample mean, so it's P hat minus P over P 1 minus P over n square root of, and that's approximately normal to 0.1 by the central limit theorem because we have a large sample here. N here is much bigger than 30. So the observed value here of the test statistic comes by putting in our 23 on 440. So let's look at the value for this 23 on 440. And that comes to 0.0523 minus our H0 value, which is 0.03 all over 0.03, 1 minus 0.03 over my sample size of 440 square root of, and I compute that, and that comes to 2.73 8. So the p-value here of this test probability that Z is, and it's a right-sided test, so it's bigger than 2.7388, where Z is a normal not-one distribution, and that comes to 0.0031. Now that's less than 0.25 or 2.5% level of significance. So we have sufficient evidence to reject the null hypothesis. So the second part is, what should the FDA do? So the FDA should increase the level of warning, in other words, make them more stringent. on the package of this drug. And the last part here was about which is worse, type 1 or type 2 error here. Well, type 1 error is when we don't reject a null hypothesis that's do reject a true null hypothesis. And so in this case, if this happens, all we're doing is increasing the level of the warning, and that's a good thing. Increasing the level of warning doesn't do any harm. Type 2 error is failing to reject a false null hypothesis. So this is more serious because here we actually should have more severe warnings and we won't get them. So that's more of a problem where you actually should be giving the drug a higher warning rating, but you aren't because your hypothesis test isn't correct. So that's all with this. You will find a quick summary over here. Have a look at that, and you should go back and have a look at excuse me, the earlier problem on the small sample size. In particular here, the situation is type 1 to type 2 error here, and which is worse needs to be discussed. We'll do this in these lectures later on. Thank you. Bye.